Welcome to another video. In last video we started talking about logic gates. We covered some of the basic gates. Two other gates I want to mention here, and both of them are very important, especially the NAND one. Okay. What is okay. So if you look at and we already know that, let's say if there's two inputs, if one of the input is 0, output will be 0. That's a unique property about AND. When both inputs are 1, then output is 1. What happens in NAND, the unique pattern that it produces is basically an inversion of AND. So whenever one of the input is 0, output becomes 1. And when both inputs are 1, output is 0, which is totally inverted of the NAND AND. So that's why what we have is AND with an inversion, and that is a NAND. So NAND symbol is then, we put a bubble there at the output. Okay. Similarly, for OR, for two inputs, the unique property of OR is if one of the input is 1, output is 1. And for output to be 0, both input has to be 0. Similarly, NOR, which is inverted form of OR, is, you can see whenever 0 and 1, as 1 is 0. In other words, when one of the input is 1, output is 0. And for output to be 1, both input has to be 0. Okay, and that is this NOR. Or another way, you can symbol NOR with again OR and a bubble at the output. This NAND gate is a very important, you will see later on in physical design. That is one of the fundamental one, because we typically use a gate. When we say it's a gate, quote unquote gate, you will see, okay, how many gates are in a design. There is a difference between gate and standard cell. We will talk about standard cells. But gate is typically, when we say gate, it means a NAND gate. So NAND is considered a kind of a basic unit on how we sometimes compare two designs. Okay, how many gates are in one? So all we do is, okay, how many NAND gates in one design compared to another one? What is the NAND area in one technology versus another technology? So that is a good kind of reflection of some of the basics in when you compare the technologies on design. Okay, so that's NAND. What you need to remember that logic gates, what they do is that logic gate transform input logic into a unique output logic. So they transform information. That is the key thing. And you have seen that each gate produces a unique output for a certain input pattern. And going back, the analogy I gave in the very first video was, okay, you have water between, there's a river, two people need to communicate, they don't have any other way, they cannot hear each other. In that example I gave, okay, there is an example of, they have some bulbs, and through two bulbs they have to communicate different things. So how can they do it? By switching them on and off, some signal can be transmitted from here. But gates is also think is the same way, same analogy. Okay, you can this person, as long as knows what those bits means, you can communicate through them. If there is a wire, and you cannot send a light, you cannot send sound, so you can use logic to communicate with each other. That's pretty much what's happening here in these logic gates. Okay, then want to take you to an example, because somebody might say that, okay, Rashid, we understand, but how you make some practical things with logic gates. So I created this example. So think of this, okay. we have three alarms. We have fire alarm. So whenever fire alarm goes, we need to inform fire department so they can come and immediately take care of the fire smoke. Whenever there is an alarm goes from the intruder alarm goes, that means some unexpected unauthorized person has entered the building, so we need to inform police. And this thing I created as a light, an alarm, as a signal, as a call, or whatever you can think of that, as some sort of indication to that department that you need to come and take care of it. Here I put this as an alarm or as a sensor. So for each one produces an output. And you know, as an electronics engineering student, that okay, you can have whenever a voltage, there has to be ground. So when high voltage, like let's say 5 volt is here, means maintenance alarm goes on. And when it's no voltage, means no maintenance alarm. Okay, so three type of alarms set up in a building, and those can inform three different departments. When a maintenance alarm goes, we need to tell it could be a device need some maintenance, something else need maintenance. So relevant company will be informed. They come and take a look. You can see that. What if all the alarms go, or one? What if two of the alarms go? Who need to be informed? Okay, when fire alarm goes, no need to tell the maintenance company to come and all that. We have a bigger problem. Okay, so fire guys need to come in and take care of that. We don't need to inform these people. Okay, well, practically police will always come whenever there's a fire alarm, but let's keep them separate. Okay. When intruder alarms goes and maintenance alarm goes, okay, which one has a higher priority? Intruder, right? We can do maintenance later on, no problem, as long as it's not that critical, like you don't have a water flowing and all that. Intruder comes in, okay, we need to take care of the intruder. We need to make sure that intruder doesn't create a problem, doesn't take away something precious. We need to tell police. So what we want to create a circuit, which is a combination of some gates, such that if all three go, the fire alarm gets a priority. So fire is only being called, and similarly the other two. The relevant priority, based on the priority, we generate a signal for the relevant department. Okay, and we need to put some logic gates in between to generate these. These outputs are, think of that voltage or no voltage type of signal. And high voltage means this is on, low voltage means this is not on. So high voltage is logic 1, low voltage is logic 0. So making things simple and talking in terms of logic level. How we do this? Let's take a look at this side, this table. This is called a truth table. Okay. We represent, okay, F means fire, alarm, I intruder, M maintenance. When an alarm goes, we say 1. When that alarm doesn't go, we say it's 0. 1 under this one means maintenance alarm is on, but intruder and fire alarm are not on. 1 means both maintenance and intruder alarms are on at the same time. So that is input. You can see that there are 3 inputs. There are 3 variables, 3 things that can change. So if you think of 0, no alarm, 1 is alarm, how many different unique combination can happen? Okay, there are 3 bits. So with 3 bits, how many combination? 1, 2, 3, 4, 5, 6, 7, 8, which is 2 raised to power 3. Okay, now if you think that this start with 0, we typically do this 0, 1, 2, 3, 4, 5, 6, 7, 0 to 7. then you can say I will go from 0 to 2 raised to power 3 minus 1. You can generalize it. So when there are n bits, how many combinations you can generate? 2 raised to power n. But if you start with 0, which represents the very first one, everything is 0. The last one, everything is 1. So the last one will be 2 raised to power n minus 1. So total range is 0 to 2 raised to power n minus 1. It's nice to remember like that because actually you will have 8 bits, 16 bits, 32 bits, or somebody might tell you, okay, I have 6 bits. What's the maximum number I can have? Or in order to have 64, how many bits I need to represent 64? You can see that 0. So look at this combination. Again, if you have already done it, it will be easier to understand, but somebody new might struggle. So I'll explain that. 0, 0, 0. So always start with every time you're changing one bit. 0 to 1, both are 0, 1. So now this bit changes. Okay, 0, 0, 1, 0, 1, 0. So, and then another way to look at this, if you look at every time the first bit is changing, but the second bit is changing after every 2. And the third bit is changing after every 4. So you can do it on your own on paper, but you will see that these are all the possible combinations when you have 3 input variables. Maybe I'll do a separate video on how you can represent some digits into binary or binary into digits and what is the maximum combinations you can have. That will help you understand. Those are definitely important concepts that I was planning to go into before I go into arithmetic, but right now I'm on logical. Okay, let's get back. We have these 8 combinations, and when we say that, okay, considering this circuit that we need to create, we have 3 outputs. So AF, alarm, fire alarm, police alarm, maintenance. When all are 0, all outputs are 0, no alarm, no problem. When maintenance, we need to call the maintenance department. When intruder, we need to call police department. When both intruder and maintenance, then we need to call the police. Not worried about the maintenance for now. And like this one, this is only fire, pretty simple, obvious. We call fire department. Again, fire department, and if one of the other one is on, doesn't matter, we will call fire department. It's an important situation that when fire department is on, you can see it doesn't matter what combination is there, its output is always AF. In other words, these things are don't care. You will hear this being said, don't care. So what I can do is I can simply even put X's there. Don't care. Maybe I just put the first one. I don't need to put anything else, right? It doesn't matter. They just repeat. Oops. Okay. For any other combination, for all these, the same thing above applies. Now, hopefully you have understood. We need to turn this into gates. So how we do that? We need to get rid of this. Give you some space here. Okay. Now we need to turn, so we need to calculate AF. So what is for AF? AP? We need to create what we call Boolean equations. Important to remember these terminologies so that when you hear it's not new. I'm of the opinion you don't stuck with that. So think of that, how we create a logic gate or logic gate combination to generate AF. Okay, AF is on, sorry, let's start, yeah, maybe AF is good, maybe AF is good. So when you see in the AF line, when it's 1, so this method we do is we only look for when that output is on. We only create a logic gate for that combination, and you will see that when we create for that, for other cases it will automatically be 0. So that's a nice way to design thing. So 1, AF is 1 when F is 1. Okay, in other words, you don't need to put any gate in between, because whenever F is 0, AF is 0. When is 1, none. So these things actually all don't care, doesn't matter, because F has the highest priority. So in this case, you can see AF is F, no gate. Or in other words, there's another gate for that condition. When the input and outputs are same, you call it there will be some delay from here to there. Information will be delayed a little because there is a wire going. So we can call that another gate is buffer. So remember, for inverter there was a bubble there, but in this case there will not be any bubble, so it's a simple. So for F, we put always inputs on this side, AF and F. Simple, a buffer. Or even if you don't put a buffer, put a line there. Okay, let's go to the next one. P. So you can see AP is on here, AP is on here. So let's create how you will form gates for that situation. Let's do that. Put a different color and make it simple. So for this one, let's look at this. It's 1 for 3 conditions, 0, 1, 0, 0, 1, 1. Okay, so here is how you write. So this one is output and these are input. Let's first write a logic gate for this one. So you can see F need to be 0. So whenever 0, you put this thing on top. I not 0 has 1, so nothing on the top. M 0, so you put this one. Okay, but there's another one, so what you do is plus. For this one you put F is inverted, I not inverted, M is not inverted. That's interesting, isn't it? So what these two means? What these two means is, this is called a min term. In min term, another terminology. Min term. Then this one is a product of input variables, like product, you're multiplying them, right? In other words, you're ANDing them. So I would say this F, this I, this M. F, there's an invert at the top, so you put inverter. There's I, no inverter. M, there's an inverter. And you AND them. Okay, let's look into this one. F, as you can understand, F has to be 0, right? So F is 1, you can look at what happens here. I this time as is, M as is. So it's a 3-input AND gate. So previously we looked at 2-input AND gate. This is a 3-input AND gate. And this plus means either this is 1 or this is 1, and whenever it's an OR, we put an OR gate. This is our AP. Okay. Let's see if this gate and we compare to this situation, it works or not. Let's say F is 0, I is 0, M 0. F is 0, there is 1, I is 0, and you know on AND gate, as soon as one of the input is 0, output is 0. So I is 0, output 0. And let's check on this side. Again, I is 0, so and M is 0, so 0. 0 and 0 into R, when both inputs are 0, output is 0. So you see that we get 0. Similarly, 0, 0, M is 1, only M is 1. But when M is 1, this gets inverted, so it becomes 0. M is 1, I is 0, so I is 0, so this is 0, again output is 0. Let's look into this case. F is 0, so this is 1, not a problem for AND gate, because as soon as one of the input is 0, output will be 0. Let's look into I is 1, okay, this is 1, this is 1, still output of AND will be 1. Let's look at is to M is 0. When M is 0, this is 1, M is 0. So what happens is this becomes 0 and this becomes actually 1. If you look at M is 0, this becomes 1, I is 1, this is 0, this is 1. So when one of the input of R is 1, output is 1, and that's exactly what we create. Same thing as this, your homework, you create for this one, and for F is 1, it will be 0 anyway. So in other words, we can say that F we just connect there, or you can say we put a buffer there. There's a delay, but there is no inversion thing. AP, you need to put this gate here. So you say and you have and these you need to connect to this. So basically this they will be connected just like this. Okay, we made AP. How do we make AM? So good thing is AM is only 1. Let's pick a different color. M only 1 1. So we only need to look into this combination. And in this combination, F is 0. So what we do, F inverted, I is 0, I is inverted, M is not inverted, is 1, so it is not. That's it, there's no other one. If we had another one, we would be doing plus and we put another product term. So in this case, this is simple. What you have, again, we put outputs here and inputs here. F comes, it's inverted, I is inverted, M as is, and you can prove that this circuit will generate 1 only when on the input we have this combination. For any other combination, this will generate 0. So we go back put simply AND gate, and again this combination is same as this one. I'm not drawing here to save time. Maybe next time before the video I will complete the circuit. So yeah, that's it. Now you put all the circuits in. Don't need to anything. As whenever the relevant alarm goes on, based on the priority, this signal will be generated. Don't need to do anything. You put that circuit in there. You can create a PCB or Vero board. You can buy these AND gates and OR gates, by the way. You can buy chips with just AND gate. I remember we did in our first or second year in bachelor, and then you put them on Vero board. Maybe next time I can pull those IC numbers and tell you. It's not, we don't do that anyway, but that's just for learning. And then you will have output. Hopefully this gives you a better way to relate a practical application with respect to gates and understand how using gates you can create a simple thing, and based on the simple thing you can create a very complex things as well, as we do in modern chips. Okay, that's all. See you in next video.